There's a really loud motorcycle. It's perfect timing. Um, it is my pleasure to introduce Joseph Skelton from Tulane, who will tell us about Koszul properties of symbolic powers of cover ideals. Joseph.
Hi. I'd like to start off thanking the organizers for inviting me to give this talk. It's a great opportunity, I think. So yeah, I'm going to talk about Koszul property of symbolic powers of cover ideals. This is joint work with Yangu and my advisor, Tai Ha. The talk's going to do the basic outline of introduce some definitions that I'm going to, and some words I'm going to say a lot, connected to a whole bunch of other stuff, and then get to our sort of motivating results and our main results in this paper. So first thing, what are cover ideals? So throughout this talk, I'm going to talk about graphs that are simple graphs over some number of vertices, and the associated ideals are going to be in a characteristic 0 polynomial ring with the same number of variables. So in general, a cover ideal, for every edge of your graph, you take the vertices of that edge, put it in an ideal, and then intersect all of those ideals across all edges. That gives you a cover ideal. This is a square-free monomial ideal. And each generator actually corresponds to a minimal vertex cover. So these do, much like edge ideals, exist in one-to-one correspondence with graphs, so you can actually characterize them off of the graph, which is a very nice and useful property. So for example, here's a graph for every edge. So x1, x2 is an edge, so it's a generator, or it's an ideal in the intersection. And then once you take this intersection, you get this resulting ideal, and you can see that x1, x3 is a vertex cover, x2, x3 is a vertex cover, and x1, x2, and x3 are vertex covers, or x4, sorry. So that's a cover ideal. Symbolic powers is a very popular topic of discussion these days. The symbolic power of I, you take the ordinary power of I times the localization of the ring at an associated prime, intersect that with the whole ring, and then intersect all of those across all associated primes. They are notoriously difficult to compute and deal with because of just all of that business. Fortunately for monomial ideals, we have a little bit of a nicer time with them. It is just the intersection across associated primes of those primes to ordinary powers. It's a little bit nicer, still can be problematic for large graphs and large powers. So I'm talking a lot about vertex decomposability. It is a property of simplicial complexes. And basically you use the del and the link of a vertex in that complex to get these vertex decomposable property. In 2009, Woodruff showed that if you consider the independence complex of a graph, you can actually translate this definition directly to the graph itself, so you don't have to look at the independence complex. And that definition is the one I tend to use the most. Says that the graph is vertex decomposable if either it's totally disconnected, so no edges, or you have a vertex where when you delete that vertex, you get a vertex decomposable graph. When you delete the neighbors of that vertex, you get a vertex decomposable graph. And no independent set in the deletion of the neighbors is maximal in the deletion of X. And this property is actually, the second property actually says that X is a shedding vertex. So any vertex that meets that second property will be called a shedding vertex. And is often useful in these types of things to show you a non-example. So C4 is not vertex decomposable. It actually meets the first condition, that if you pick any vertex, say x1. If you delete x1, you get a path that's vertex decomposable. If you delete the neighbors of x1, you get a single vertex that's vertex decomposable. So it meets the first condition. The problem is the second condition. So if I delete x1, I get this path, but then the neighbors consist only of x3, which is a maximal independent set in G naught x. So C4 is not a vertex decomposable graph.
Sorry, this is, I don't think about graph theory this often. So when you say neighbors, you don't mean X itself. You mean like everything around it, but not X.
In this case, we actually do mean X itself. The closed brackets means
Okay.
the neighbors of X and X.
Great, thanks.
Yeah. So we will also be doing a lot of whiskering graphs. So the process of whiskering a graph is to introduce a new vertex and then connect it to a vertex in your graph. And you will say that that vertex has been whiskered. So as an example, just take a graph. If I want to whisker x1, I introduce y1 and connect it. So that graph is now whiskered. And what is nice about this whiskering process is it actually forces the vertex you whisker to be a shedding vertex. Because whenever I delete x1, I isolate y. So that would have to be included in any maximal independent set. But y is deleted whenever I delete the neighbors of x. So you actually force that condition, which is a really great tool to use. So what are Koszul modules and why do we care? So Koszul algebras were introduced by Priddy in the 70s. They were generalized to Koszul modules by Herzog and Iyengar in 2005. They've also been referenced and used extensively by lots of people under various names. So they have a very long history. But basically they are a finitely generated R module and its associated graded module is a direct sum with respect to the homogeneous maximal ideal M of R, and it has linear resolution over the associated graded ring. And being a Koszul module has implications in two other things, mainly the Golod property. So an ideal is Golod if the Koszul complex of R mod I with respect to the variables in R admits a trivial Massey operation. And to kind of bring this back to symbolic powers, Herzog and Hünicke in 2013 actually showed that in a characteristic zero over a characteristic zero field, and I is a homogeneous ideal, then the ordinary and symbolic powers are Golod. Another related concept is component-wise linear ideals. So an ideal is component-wise linear if each degree component has linear resolution. And in a polynomial ring, component-wise linear ideals are Koszul ideals and vice versa. So all of this is to say, this kind of makes you want to wonder, can we find polynomial ideals that are whose powers and symbolic powers are Koszul? Because it will obviously just give us a whole bunch of stuff. Another topic is sequentially Cohen-Macaulay modules. So this is the non-pure version of Cohen-Macaulayness that I believe Stanley introduced. So M is a graded submodule of R if M is sequentially Cohen-Macaulay. If there exists a filtration where the quotients increase in dimension and the quotients are Cohen-Macaulay. So this has a relation to whiskering because in 1990, Villarreal showed that if you whisker every vertex on a graph, then that graph is Cohen-Macaulay. And then Francisco and Ha in 2008 showed if you whisker certain subsets, then you get sequentially Cohen-Macaulay. So if you loosen the restriction on the vertices, you get a little bit looser definition of Cohen-Macaulayness. And sort of the unifying theorems here, how it's kind of all comes together. In 2009, Woodruff showed that vertex decomposability implies sequentially Cohen-Macaulay. Romer and Yanagawa showed that a homogeneous ideal is Koszul if and only if it's component-wise linear. So that's the polynomial ring citation for the earlier statement. And Herzog and Hebe and Yanagawa showed that the cover ideal, which is the dual of an edge ideal, is component-wise linear if and only if the graph is sequentially Cohen-Macaulay. So it's a whole bunch of stuff that's all connected in my like weird rope on the board way. So whiskering a graph, we can force vertex decomposability onto a graph. That will then give us sequentially Cohen-Macaulay, which in the polynomial rings that I'm working with is equivalent to the cover ideal being component-wise linear and Koszul. So we have that entire right half. My main focus is on the whiskering and the forcing vertex decomposability onto a graph. So the problem here, or the question is, well, this is for a cover ideal, what do we do for symbolic powers of a cover ideal? Well, there's some results for this. If you, Dung, Hein, Nguyen, and Trung showed that if you whisker all vertices of a graph, then all symbolic powers of the cover ideal are Koszul. Salvaraja showed if you whisker a vertex cover, then all symbolic powers of the cover ideal are Koszul. And then last year, Kumar and Kumar showed if you have a unicyclic graph, so that's just a cycle with some attached forests, if you have a whisker on the cycle, then all symbolic powers are Koszul. And they did this, or one of the tools to do this is this graph construction that was introduced by Fakhari, which basically introduces this new graph GK, G sub k. And the way you construct it is you take your original graph, you copy each vertex k times, and then you connect the vertices if they were originally connected in the graph, and the second index, the second indices add up to at most k plus 1. And what he showed is that this graph is the cover ideal of this graph is the polarization of the symbolic power of the cover ideal of the graph. There's 4 ofs in that, so you know it's good. And what this looks like, because this definition is not, can be kind of confusing. So what this means is if I want to take C4 and I want to find G3 of this graph, I'm going to copy each vertex 3 times, give it a secondary index just to keep track. And then because x1 and x2 were connected originally, there are edges connecting these under the condition that the second index is at most 4, which means I can also connect these. But I cannot connect x12 to x23 because it's the second index is too big, or x13 and x23 because the second index is too big. And then if you do that for everything, you get a graph that looks like this. The GKs can get very big and very unwieldy very quickly. But they look really cool. This graph has actually been given slightly looser restrictions by Kumar and Kumar. They construct a graph in a similar fashion, But instead of doing it to the whole graph at once, they do it edge by edge. So for a single edge E, give it a K. Then you copy the vertices the same way. You connect the vertices the same way for each edge. And then you take the union of all of those constructions, and that gives you this G K vector, or G vector K. So what does that look like? So same idea. I'm going to take C4, label each edge, E1, E2, E3, E4. If I want to find G1322, so then I copy the vertices of edge 1 once and connect them so that the second indices is at most 2. So that's done. For edge 2, I introduce 3 vertices, or I introduce the vertices of that edge, connect them the exact same way we did in Selvaraj's example. For edge 3, do the same thing, but this time because it's 2, you only need to introduce 2 copies. And because these 2 copies were already here, just use them. And then for edge 4, do the same thing. So this is a really nice construction because it lets us work with each edge individually instead of the whole graph at once. And if you let all of the k's be the same value, then gk vector is the same as g sub k. So some useful tools that I'll be using. So this was in Selvaraj's paper. It's a way to basically prove a graph is vertex decomposable without having to go through the g naught x and g naught the neighbor of x are vertex decomposable however many times. So the idea is give yourself a sequence of vertices, z1 to zm, then define psi I to be the deletion of the first I vertices in your sequence. And then omega I is the deletion of the first I vertices in your sequence and the neighbors of the ith vertex in your sequence. So if zi is a shedding vertex when you delete the preceding zi's, omega I is vertex decomposable for all I, and psi m is vertex decomposable. So you don't need psi I, you just need the very last one when you delete all of the vertices in your sequence. To be vertex decomposable, then your graph is vertex decomposable. So kind of how this works. Oops. There we go. So if I define if I have a graph and Z1 and Z2 are my sequence, Z1 is a shedding vertex because it's whiskered, and so that forces the sheddingness of it. If I delete Z1, I get this graph, and now Z2 has a whisker on it, so it's a shedding vertex. So the first condition is met automatically, or already. The last condition, so if I delete Z2, then I get a path and some isolated vertices, so that's vertex decomposable, so the last condition is met. And then for the second condition where I start deleting neighbors, so if I delete Z1 and its neighbors, that deletes all of these, and I get a path, which is vertex decomposable. And then if I delete Z1 and the neighbors of Z2, I just get a nice single vertex. So that's vertex decomposable. And that's basically how Selvaraj's theorem works. Is you just need to look at a couple of things related to your sequence, and you're good. So now we get to the stuff we proved. And a lot of these kind of lead towards making the proof of using Silver's theorem a little simpler. So first, if you have a graph with a whiskered vertex at x1, or any x really, just for the sake of indexing, then if you copy that whisker km times, then when you delete the first I-1 copies of x1, xi is a shedding vertex. And this effectively shows that a whiskered vertex maintains a sequence of whiskered, how do I say this? The copies of x1 as a sequence satisfy the first condition of the omega psi lemma. To see that, this is the K2 of that first example I drew, the first example I had. So that's G. And then we have G2, and I've highlighted the whiskered copies. So X1, or X11, has a whisker on it because the last copy of the leaf vertex of Y only connects to the original vertex for any combination of this. So it's always, so X11 is always leaf, always has a whisker on it. So it's a shedding vertex. And then if I delete X11, I delete some extra edges, which introduces Y11 and puts a leaf on X12. And this will just continue down the line. Basically, X11 connects to Y1K, and then they just kind of go back and forth to each other as you go up in indices, in index. The other thing we show is that basically when you start deleting vertices, we start deleting copies of a vertex, you reduce the number of shadows of edges, or the copies of edges. So if you have an edge connected to your vertex with this vertex in it that has been copied less times than there are copies of your vertex, then you will at some point just effectively remove the edge from the graph. So that's what this first part says. If you delete enough of these, you remove the edge from the original graph, and you no longer need to worry about it. If their edge is copied enough times, you simply reduce the associated K, or KT, by however many copies of your vertex you deleted. So this shows that when we start deleting vertices in omega, or in omega, we're really just reducing the number, the KIs throughout the graph. So to see how that works, again, same graph. When I delete X1, or when I delete X11, I reduce the copies of I reduce how many copies of these edges there are. So there were 2 copies of those edges, now there's 1. If I delete X12, then I delete both copies of this edge, of these edges, and have effectively removed them from the graph. It's as if they were never there. Okay. So our main result, we talk about a cycle cover. So a cycle cover is just a subset of vertices where every induced cycle has a vertex in that subset. So if S is a cycle cover, then for any k vector, If the ki associated to the whisker is at least any kj associated to an incident edge, then the G union the whiskers at that set for whatever k-tuple that meets the criteria is vertex decomposable. So essentially just copy the whisker more than anything else around it, and you're good. If you do that, then you can have them all be equal, and the corollary gives you that the cover ideal, all symbolic powers of the cover ideal are Koszul. Just like we wanted from the very beginning. The proof of this, just kind of in a very hand-wavy fashion. So we let the sequence just be, take a whiskered vertex, whatever one you want. The sequence is all copies of that vertex. And then induct on the number of cycles. So because we copied the whisker more than anything else, we ensure that the first condition of the omega psi lemma is met. And so that's the, because the whisker will always be there to ensure the shedding vertex. In psi k, when we delete all of the xi's, if we delete all of the all the copies of x1, sorry, if we delete all the copies of x1, then we remove any edge that it's incident with, including a cycle edge from the original graph. So by induction, we have reduced the number of cycles. So it is vertex decomposable. And for omega I, this one is a little trickier but we use the fact that the neighbors of x1j are a subset of the neighbors of x1i for any I less than j. And that's just from the construction, because the second index has to add up to most k plus 1, the bigger j forces the neighbors to be a subset. Because of that, whenever you delete the neighbors of x1i, you isolate all the remaining copies of x1, effectively removing it from the graph, from the original graph, meaning you reduce the number of cycles, so by induction. Then, that's essentially how that proof works. We also have a gluing theorem. I won't read it to you, I promise. What this basically says is if you have two graphs with a whiskered vertex that meet the criteria of Selvaraj, where like all copies of that one vertex meet the criterion, then you can actually glue those graphs together along the whisker. You don't need a cycle cover or anything like that, just as long as you have that one sequence of that one vertex works in both graphs, glue along the whisker, and you're golden. So what does that look like? How does that work? You get well, my brain just stopped working. Okay. Take this graph and this graph. They each have a whiskered vertex. I know x1 works as a sequence whenever I start taking gk vectors because of our main result, because x1 is a cycle cover in both of them. Haha, I cheated. Then I can glue along this whisker to obtain a new graph. And then that new graph is vertex decomposable. Again, you can use the vertex you glued. So in the future directions, can we get similar results for simplicial complexes? There's, I believe, Bierman, Francisco, Ha, and Van Tool, if I remember the paper correctly, gave conditions for a simplicial complex where you get vertex decomposability, and it relates to the graph. So can we get kind of a similar whiskering effect? Is there a smaller subset? So we used a cycle cover, but there are graphs where all symbolic powers are vertex decomposable, but don't have a whisker on every cycle. And can we get necessary and sufficient conditions? So this kind of goes back to the, can we get a smaller set? That's kind of where my thoughts are headed right now. Thank you.
All right, let's thank Joseph. Questions for Joseph? While we're waiting for questions, would you mind scrolling back to the, I guess you have two main theorems, to the first main theorem?
This one?
Nope, a theorem.
Oh, the main theorem, yeah.
There we go. Thank you.
For like the simplicial complexes, what would be the, what would be the analog of whiskering? Would you be putting on like a facet of the, of a dimension that I mean, I don't, I just kind of want to have an idea. What would be, what would you use instead of whiskering?
So whiskering, kind of looking at the independence complex of graphs, I guess. So the whiskering a graph is analogous to partial colorings in simplicial complexes. And so kind of looking at that, like, are there partial coloring restrictions we could do? I think it's we're still early stages in thinking about that, I think.
Also earlier, I mean, you had some comment or definition about the symbolic power of monomial ideals. And I felt like it should have been square-free monomial ideals. But I mean,
That's correct.
you don't need to go back to it, but I think
yeah,
it was
you're
supposed
right.
to be square-free.
You're right. Thank you.
Joseph, I have a question. So the cover ideal is the Alexander dual of the edge ideal and vice versa.
Mm-hmm.
So getting these results for symbolic powers of cover ideals, are you getting any new information about edge ideals by Alexander duality?
It's possible. I don't think we've actually looked at that.
Sure.
That's a really good question.
Thank you. My second question is, so you're getting the fact that these symbolic powers are Koszul, so that's characteristic independent. Is that correct?
Mm-hmm.
Is that true in general, that for a square-free monomial ideal, the symbolic powers being Koszul is characteristic independent? I'm always keen on these things where you can get algebraic information from the combinatorics, and then as a consequence, you get characteristic independence.
I would need to look back, but I think I'm always hesitant to say you can just let characteristic be whatever.
Right.
Yeah.
Okay.
But it's possible in certain, for Koszul at least, it might be possible.
Okay. Thank you.
Yeah.
Other questions for Joseph? All right, let's thank Joseph again.